So let's see if we can do this, number 20. I guess my first thing I'm going to do is just write it down, huh? So I have little r of t. And again, this I should probably also write down that this is section 13.7. Little r of t is equal to 1 plus 3t is the x coordinate, and then 2 plus 4t. All right, so this is in 2 space. Okay, and they're saying here AB is 0, 6. So what I'm going to do is I'm going to say 0 less than or equal to t less than or equal to 6. Okay. And then the other curve, capital R of t, I'll do it in a different color. And that's the function defined by the vector 1 plus 9t, comma, 2 plus 12t. And here,
Can you move it down one?
yep. I'm going to do a lot of moving here in a second.
All right.
I'm just trying to get it copied down for myself, really. It says on CD. Oh, we have to find CD. I see. So the question is, what should be C and D? Right? Well, let's see. I guess we want, 1 plus 3 times 0. Let me go ahead and do a little work over here. We want 1 plus 3 times 0 to be equal to 1 plus 9 times c, right? So if I solve, I guess I want c to equal 0. Yeah. And then similarly, I can write down that we want, what would the other equation be? 2 plus 4 times 6, we want to equal 2 plus 12d, right? Because we want these to be tracing out the same path in much the same way that I had that today with the lines I had before. So I guess we work this out and we get 2 plus 24 is equal to 2 plus 12d, so it looks to me like we want d to equal 2, right? So we're going to go for capital R between 0 and 2. Okay, so there's my answer for part A, I guess. Jimmy, this all right?
Mm-hmm.
Okay. Part B. Oh, I got to put that back up there. Find the velocity for both objects. Well, okay. You could do that, right? I mean, we're going to compute r prime. So r prime of t is the vector 3, 4. And capital R prime of t is the vector 9, 12. Oh, so what's the difference between little r prime and capital R prime? I mean, I guess from a picture-wise, right? Little r prime, 3, 4 looks something like that. If we move 9, 12, that's the same as 3 times 3, 4. So this is just kind of 3 of these together would be 9, 12. That's the picture, right? You have 3 times as much velocity for the second parameterization as you do for the first. Part C, graph the speed of the two objects over these intervals respectively. Okay, well this one's kind of boring, right? I mean, compared to maybe some of the other exercises I could have assigned. So part C, how do you compute the speed? Well, the speed of r of t would be given by the magnitude of r prime of t. And you could use the formula, but you're just going to get 5 because it's a 3, 4, 5 right triangle. And similarly, r prime of t, right, I guess would be what? 15, right? 9, 12, 15. And so I guess if I had to sketch a graph, because it asked me to, and like I said, it's kind of boring. Here's the axes. Here's t. And so here's 5, right? The speed's always 5. And then here's 15. So what I imagine happens is that usually when you compute part B for the other problems, you don't get a constant. And it's, you don't get, because the functions aren't linear. Do they have, yeah, so like plenty of problems here, the functions are not linear. 20 just happens to be linear. Okay? Any other questions on the early problems? Yep.
30?
30?
Yeah. Was it orthogonal?
20 or 30?
30.
30. So it's, oh, you guys know what the word orthogonal means? Perpendicular, right? Okay. Determine whether the following trajectories lie on a circle in R2 or a sphere in R3. If so, find the radius of the circle or sphere and show that the position vector and the velocity vector are everywhere orthogonal. Wow. If you solved problem 30 correctly, you didn't know this, but you were learning the next section. You're learning about curvature. It turns out that this circle you're trying to find, or this sphere you're trying to find, is called the osculating circular sphere. So I'll come back to that maybe after we work on it. Let's see what we can do here. All right, so I guess we're in 3 space here, right? All right, so let's see what's going on. This is number 30, and I will move this over so you can see it a little better. R of t is equal to, and again, the bracket notation is a lot better, so we have square root of 3 cosine of t plus the square root of 2 sine of t, comma, negative square root of 3 cosine of t plus square root of 2 sine of t, comma, square root of 2 sine of t. Who knows what that curve looks like, right? And we're going from 0 to 2 pi, which is nice, because I know that the period of cosine and sine is 2 pi, so what's going to happen to this curve? This is what you call a closed curve, right? It's going to do something here. It's going to close. Find the radius of the circular sphere and show that the position vector and the velocity vector are everywhere orthogonal. All right. Well, I guess how do you show that something is on a circle or on a sphere?
Show that its velocity is always orthogonal to its acceleration.
Well, that's what they said to do secondly. They said show that second. They said first show it's on a sphere, then show that. Show that velocity and acceleration are. And actually, I'll tell you right now that I did show you how to show that the velocity and acceleration are orthogonal, right? We used a dot product, and you have to show that the dot product is what? Is 0. So that would do kind of the second part. But maybe the first part got you. I don't know. Here, let's show that this point is always on a sphere centered at the origin, centered at 0, 0, 0. How do I do that? Well, I need the equation of the sphere, which is what? That's what I get for doing problem 30. Try again. Let's backtrack. Pretend that I had assigned, here, problem 25. Oh, I did. All right. What's the equation of a circle? X squared plus y squared equals r squared. All right, let me try this. I'll do 25 in my head. X squared would be 64 cosine squared of 2t. Y squared would be 64 sine squared of 2t. I'm going to factor out the 64. So it's 64 times cosine squared plus sine squared, which is 1. I don't care if it's about the 2t anymore. It equals 1. So it's 64. So this is a circle where you have x squared plus y squared equals 64. So that's a circle of radius 8. Same idea here, guys. For number 30, we're going to do, what's the equation? X squared plus y squared plus z squared is what I want. Does this make sense? So let's see if we can do it. Should I work it all out? Yes, okay. So here we go. I think it is worth showing you this. I was just talking to Math 0950. Oh, I think I told you guys that, right? I made them swear with right hand extended. When you square a binomial, you get a trinomial. All right, good. The last one is just a monomial. All right, so I think I can work that out. Let's see if I can do it. When I square this guy, I get 3 cosine squared t plus 2 radical 6 sine t cosine t plus 2 sine squared t. So that's this piece right here so far. And now I'm going to work out this piece here. When I square that, I get another positive 3 cosine squared t plus, oh no, there's a minus, right? So it would be minus, is it 2 radical 6 again? Yeah, because it's radical 6, we have to double the product. 2 radical 6 sine t cosine t, and then it would be plus 2 sine squared t. That's nice. And then when I square the last piece right here, I get plus, that would be 2 sine squared t. Yeah? So when you work this all out, well, these guys drop out right here, right? You get 6 cosine squared t plus how many sine squareds? Yep, this is 6 sine squared t. And so again, factor out the 6 from cosine squared plus sine squared, and you get 6. So we just showed that x squared plus y squared plus z squared equals 6. And so this curve is on a sphere of radius square root of 6. Are you with me? So what's the rest of it? Well, if we want to show that the velocity and acceleration vectors are perpendicular, I need to compute them first. So I'm going to compute r prime, then I'm going to compute r double prime, and then what I'm going to do is I'm going to do r prime dot r double prime. And when I dot them, I hope I get 0. So that's the rest of the game. So we're going to, that's not what we're doing. We don't need r double prime because they don't say to do that. They say look at position and velocity. And so then what we will do is we will show that r dot r prime equals 0, and then we're in good shape, right? All right, so I'm ready to do that. All right, so what is r prime? It's negative radical 3 sine t plus radical 2 cosine t, comma, and then the next piece, and how'd I get that? I guess I got to show this whole screen here, right? I'm taking the derivative just component-wise, so I just did that first piece. Now I'm going to do the second piece, and so I'm going to get positive radical 3 sine t plus what? Radical 2 cosine t. And then I get radical 2 cosine t. And now this is fantastic. I have to dot these two things? That is so cool. I mean, I have to, how do you dot product? See those things right there? Those are binomials that I'm going to multiply. Then, my next step will be to multiply these binomials together, right? And my last piece will be to multiply, well, these monomials together, right? Tell you what, I'll do the monomials. I get 2 sine t cosine t. Let's add that to what you guys get when you do the
0.
Well, all the rest adds up to negative 2 sine t cosine t, clearly, right? So, all right, I'll do a little bit more. Do you want me to do pink or green? I'll do pink. Here we go. Here we go. How do you multiply these binomials together? First, I get negative 3 sine t cosine t, and that comes from first. And then outer would be this thing times that thing, so I get minus radical 6 cosine squared t. And then inner, I get plus radical 6 sine squared t. And then last, I get plus 2 sine t cosine t. Wow, there's a plus 2 sine t cosine t there, just like one here. I wonder if I actually get minus 4 sine t cosine t in the other piece. I hope so. Oh, I get plus another 2, but then I get minus a 6. No, minus a 3. It does work. Wow, that's cool. That's enough. Does anyone have a nicer solution that they want to post up here for all prosperity? That's what I thought you'd say. All right, we'll let the home audience work it out.
I have it worked out.
Yep. Okay. Let's do 70 and see where that takes us. A golfer stands. I can't wait for summer now. Yeah. So this is getting me excited. So, what angle should it be hit to land in the hole? Okay. And so, we're picturing theta for my angle. Is that okay? Well, right now I can't see anything, so let's move that. Okay. And what we know is we know that the ball takes off, okay, with, I guess what we know is we know the length of V naught, right? We know the length of V initial. We know that after you hit the ball, it's going to take a parabolic path, right? You could say we understand that from physics, or you could say we understand that because we read the section, and we worked out some of those formulas with you. But the basic idea is that, again, R of t here is going to be given by the length of V initial, cosine of theta, and the length of V initial sine theta is almost the correct y-coordinate. The only issue is now what do I have to subtract? I need to subtract the effect of gravity, right? So we subtract 1/2 gt squared. And by the way, these things are times t also. So maybe I should put a t in front of this quantity and a t in front of this quantity. So, you know, if there were no gravity, wouldn't that be an awesome golf shot? You know? You would just have this linear function where the cosine and sine tell you exactly where it's going to go. It gives you the slope, y over x, right? But that's not the case. We have this gravity which pulls it back down, hopefully right into the hole. And so viewing this problem, I guess what I want is I want to put my axes in a smart place. And so I'm going to say that, you know, here's the origin, right? 0, 0. And they tell me that the hole, what'd they say? I'm 40 feet below the hole right now, and I'm 130 yards away, which is 390 feet. So if I'm working in feet, then this could be the point 390, 40. Yeah? And so I think I'm ready at this point to try and write down what I need. Basically, we want the correct angle, the correct t and theta, because we don't know either of those. We want the correct t and theta such that r of t will equal 390, 40. Do you think if I turn over my scorecard this summer when I play my son and work this out, that'll help my game? Because I could. I don't know. So, but this is what we want, right? So basically we want the x-coordinate to equal 390 and the y-coordinate to equal 40. Guys, that's two equations, two unknowns. It's a no-brainer. Well, no, these are not simple to solve. Let's look at them. Look at the system a little more carefully. So we have t times, we know v naught. What's v naught? It is feet per second, so we can just say 150, right? Because it's feet per second. We're talking about, you know, x or y and then t. So that's good. So so we could say that the equation is t times 150 cosine of theta is equal to 390. That's equation number 1. And equation number 2 would be t times 150 sine of theta minus 1/2 gt squared. So let's see, that would be g is 32, right? So 16t squared, this has to equal 40. And so in theory, if I can solve these two equations, I'm in good shape. Of course, one issue is that I have sines and cosines. So I like squaring both sides. I like replacing t with cosine of theta. Well, I mean, So now I have to think about best practice for the rest of this. Boom. All right, let's try this. Let's try solving for theta here. Okay, so the cosine of theta is equal to, well, 39/15 t to the negative first, right? Or you could write it as 1 over t, I guess. In other words, theta is the arc cosine of what? Of 39 over 15t, right? Now I come over here, substitute in.
39 over 15 is 13 over 5. It's a 5, 12, 13.
Oh, that's beautiful. So here we go. T times 150 the sine of, I'll just say theta. So yeah, what is this sine of theta? Let's see a picture. Here we go. Like you said, this, Kathy, this is the arc cosine of, if we divide top and bottom by 3, we get 13 over 5t, right? So the picture looks like this. Here's theta. Boy, if it weren't for that t, I'd be so much happier, you know? Oh, but the t's gonna...
You moved the.
it doesn't look very good, so yeah, I could. All right. I guess what I'm seeing, if the cosine is 13 over 5t of theta, this is 13, this is 5t, so this is the square root of 25t squared minus 169, yeah? Does that make sense, or is that too fast?
That's fine.
Yeah, but you already solved the problem.
Well, I didn't do it this way. And I didn't solve the problem.
That's
I got
a good point.
73 degrees.
What? Okay. You guys okay with how I got that? I just Pythagorean theorem, right? So once I get that, then I'm going to replace that sine of t, or sine of theta right here, okay? This is going to be replaced by an expression coming from that triangle. It's funny, you're talking about trig sub. That's really what I'm doing here. Makes sense, right? So my equation is now t times what? Times the square root. Oh, wait, I have 150 also. I'll put that up front. 150t square root of 25t squared minus 169 over 5t minus 16t squared is equal to 40. So I get some canceling, right? And basically what happens if I set this side equal to 0, I get 16t squared on this side. Over here there's some canceling that happens. And so I get minus 30t square root of 25t squared minus 169 plus 40. Wow. Okay. Let's do something. 2 minutes left, huh? Desmos or now let's pull out graphing calculator, guys. I have to do something here. Did it say I'm allowed to use technology on this problem?
No, it didn't deny it.
It didn't deny it. Let's see what we have. So let's type in 16x squared minus 30x times the square root of 25x squared minus 169, close parentheses for the square root, plus 40. Let's sketch a good graph of that. Nice graph. Let's think about the window. T. How many seconds is it going to take? Between 0 and 10? Yeah, well, wait a minute. We want this thing to equal 0. How about we try good old zoom fit? Hit up. I mean, okay, that's a little better. So somewhere between here and here. What's my window now? Oh, I see. I see. We really zoomed out to see it. So I'm still going from negative 10 to 10. Let me go back to zoom standard and just realize that I couldn't see anything. but I might be able to compute a 0. Second, calculate a 0. Left bound, let's say it's going to take more than a second for my golf ball to get there, and right bound, let's say it's going to take there's a 0. 2.62 seconds. Okay. So if I throw that in, here I could compute the arc cosine, and then there. Boy, that'd be nice if that's the answer, huh? Yeah. Well, it's 11:50. I have to stop. I'll check it out and get back to you guys next class, okay? Or maybe we'll make a little announcement too. That'd be nice.